for at least for now, if the integram, so if we talk about that sometime because so we have C sub 1 to C sub 2, we have F, C, B, C. So it will be independent of path over a region if the path connecting C sub 1 to C sub 2 are all lies within the region that F is analytic. So it's always, if it's analytic, then any loop is zero, then it means that any path, the integral from C sub 1 to C sub 2 will be the same. Okay, as long as the integram is analytic. So in this case, the integram is cosine to zeta, which you can say FC now is cosine to z, right? All you need to do is to show that cosine to z is analytic. Okay. And then if it's analytic, then it's then it's then the integral then how to show this analytic? So the question asks you to show for a certain path. Now the question with specifically C sub 1 is pi 1 plus I, right? That doesn't matter. It's just a given point, and then this C sub 2 is just called Z. That also doesn't matter. So this is Z, this is what your initial point. As long as this function is closed path is zero is due to the Cauchy integral theorem. As long as you show that within this region, this F is analytic, then any closed curve is zero, any closed path loop integration is zero, then any path connecting the 2 points will be independent of path. Can you see that? Because like if you have a path loop going like that, this going to C first and then going back to C sub 1, then this will be zero. But you can reverse this direction and say that the integration from here along this path is the same as going along the other path, right? Because that will cancel this path and make it zero if you go in. See, it's the same thing. It's just saying it differently. The loop integration is zero is the same as saying that the path integral is the same. It's the same. It's the same. And then to show that is the closed loop is zero, required to show that the integram is analytic. And you know how to show this analytic? That part is it easy for you? To show that the integram, this function is analytic. Yeah, Cauchy-Riemann condition. You can use the Cauchy-Riemann condition. Yeah.
You also finalize the global answer and then evaluate the answer derivative.
Well, that is like what I said last time. I think I get the example that still require you to show that the antiderivative can be multivariate. So you want to make sure that these paths, if path 1 and 2 connecting is independent, as long as they're staying within a region that you can deform path 1 to path 2 without causing any singularity. If you pass any singularity from 1 to 2, then the path integral will not be the same, or you can say that the antiderivative is multivariate. It's not the same value. So that's why last time I talked about how do you So you try to write this as u x y plus I v x y, right? Right, and z is x plus I y. So you try to make it real, and then imagine it, totally imagine. But, you can do that by using the I mean, there are different way to do it. One way to do it is to use the Euler relation. So, like you have cosine PZ is 1/2 of e to the I 2z plus e to the minus I 2z, right? And just following the exponential functions of e to the I 2x plus I 2y, but your I times i's become minus 2y, right? You see what I'm saying? So, I mean, 2c is 2x plus 2iy, but you multiply by I, so the second term becomes minus 2y. Right? You see that? Okay. If you cannot follow any step, just stop me, okay? So, and then the same thing here, minus I dx. And then you have a minus something plus 2y, right? And then follow the rule exponential function, take this out, e to the minus 2y. And then this becomes a total phase, multiplied by this factor, which is a total phase, which is cosine 2x plus y. So that's this term, and do the same thing for the other terms. E to the 2y cosine 2x minus y sine 2x. Okay. Now this time this is real. This time that is totally imaginary. Like right, this time this is real. This time that is totally imaginary. So u will be this time this plus this time this divided by 2. That's u. Okay. And v will be like this time this without the I. This time this one and this plus this time that one. Oh, including minus and without the I divided by 2. Can you see that? Now you ask me how to separate in the real part and imaginary part. Following this step, you can get the real part and imaginary part. Is it clear, Henry? Is it? Is it okay? Do I need to write it down? Okay. So u will be 1/2 of e to the minus 2y cosine 2x. You don't have. I mean, this is recorded, so if you forget it, I will post it online after the class. So you have that. Maybe that you will be the real part distance is plus this time that divided by 2. That's the real part, and the imaginary part will be 1/2 e to the minus 2y sine 2x minus e to the 2y sine 2x. I mean, they have the same factor. You can take the factor out, that doesn't matter. Right? That will simplify your calculation. Right? Is that okay? No, that. Okay, now then the next step would be to check the Cauchy-Riemann condition using u and v. Is that okay? But yeah, that's another trick that we usually don't talk about because we divide the Cauchy-Riemann condition ux is of partial x as partial v partial y, and then partial u partial y is minus partial v partial x. I mean, that is fine. This is the usual, most common way of writing the Cauchy-Riemann condition, but you can combine it to actually going back to your derivatives. Just say you can say partial u, instead of u partial u, you say partial f partial x. That will give you this one, and then that give you because you want a y, so I times this will be partial f. That is the same. This will be the same as the 2. F is the integral. If the question, the capital F is the integral, you're showing that this is a function which defined by this integral that has a z here, and you're showing that that should be independent of path. But to show that this little f, which we define as this function, this is the integral. You define this little f as this one, not in the textbook, but you define it yourself. And then you want to show that within a certain region it's analytic. And after this, you can check the Cauchy-Riemann condition and convince yourself that this is an entire function. So it is analytic over the whole complex spring except infinity. Like that is an entire function, which means any path you want to go, that would be independent of path. This integral will be independent of path. Okay, that's the argument. Is that okay? Yeah.
I don't know. I mean, what I did is I took the cosine to zeta or whatever, broke it down using Euler's formula, and then is it safe to say that because there's no singularities in that, it's just analytic?
Yeah.
With the 2 exponentials.
Yeah. After a while, you can say that obviously this is entire function because we learned that. But this is an exercise. So the exercise just asks you to show this is analytic, and to show that this is analytic, you just go through the process. Okay. Did I go wrong? So F is u plus iv. Right? If you substitute u plus iv here, then the partial u partial x is partial v partial y, and partial v partial x will be minus because the I times I is minus. Then I mean, this is the combining these two is the same. These two are equivalent. I'm just saying that if you don't want to separate in the real part and imaginary part, you can check exactly this one using the compact notation here. You can check one equation using compact notation, but keep in mind that your z is given by this. So when you take the partial derivative, you need to be able to. I mean, that will simplify a little of that. Right? If you use this, it requires you to separate the function into real and imaginary part. That is not difficult, but take a little bit steps. If you don't want this, you go back to the other way of expressing the Cauchy-Riemann condition and do it directly using f given by this. That may save you some time if you like. This is not including. I don't think the text will talk about this, but that is exactly the same. Okay, if you are lazy, just like me, you can do. Yeah.
You just put
directly using the integral. That's a no. I don't know how to do that because that requires you to integrate that along many paths, and how do you exhaust all paths? That is the question. The question asks you to show that it's independent path, but there's infinitely many possibilities. How do you check that? Then the way to do this argument is to use the Cauchy integral theorem, because if it anything over a region, then all the path, all the loop integral is 0, meaning it's independent of path. So basically, the bottom line is this question is just asking you to show the integram is analytic over a certain region. And in this case, it's the entire function is analytic over the whole complex Q except infinity. Okay. So that's a way. Maybe there's a way. I don't know. I haven't thought about it. I mean, how you exhaust all possible paths. Okay, did I answer the question? Then once you show the independent path, then you can choose to evaluate f at pi r. You can choose any convenient path, right? So from here to get to z equals to pi r, you can choose differently because the initial point is 1 times this is pi. This, I mean, imaginary part is that. Initial point is this. You want to get to the final point as just pi I, right? Just pi. So basically, you can go along this line and do the path integral, which should be straightforward, right? Or another way, Vincent thought is okay. Now, because you show that it's analytic, then you can get the entire derivative and then evaluate the entire derivative. That is also acceptable. Yeah, that is acceptable because the argument is if first you show that it's analytic, there's no singularity in the plane, then the anti-derivative is unique, then you can use that. Then just go back to the fundamental theorem of calculus, and you can do that. That is acceptable after you argue that it's analytic. Okay? Yeah. I mean, otherwise, you can just do a path integral of this along this path. That should be also true. That should not be. Yeah, for us, we need to argue that because we're just learning this, so we just the whole thing is to practice to identify analytic function, but after a while, obviously, sine and cosine are entire function. You know that. Okay. All right.